467 cubic inches of pure, fire-breathing American muscle, getting absolutely embarrassed by a 327 with parts from a scrapyard. This wasn't supposed to happen. But in dusty drag strips across America in the late 1960s, it was happening every single weekend. Picture this. It's 1968, and you pull up to the staging lights at Lyons Drag Strip in Southern California. Next to you sits a pristine Chevelle SS 396, its massive big block barely contained under that cowl induction hood. The owner spent $3,000 on that engine alone, about $25,000 in today's money. You're sitting in a beat-up Nova with a small block 327 that you built for $600, using heads you literally pulled from a wrecked truck behind a Chevy dealership. The flag drops. 8 seconds later, you're watching his taillights disappear behind you as you cross the finish line first. This is the story of how backyard mechanics and weekend warriors discovered an engineering secret that General Motors' own engineers had overlooked, how the right combination of junkyard parts and basic physics could make David consistently beat Goliath. It's about the moment when horsepower stopped being about how big your engine was and started being about how smart you were. The late 1960s were the golden age of American muscle. Detroit was locked in a cubic inch war that bordered on insanity. Chrysler had their 446-pack and 426 Hemi. Ford was dropping 428 Cobra Jets and 429s into anything with 4 wheels. And Chevrolet? They had an entire catalog of big blocks, the 396, the 427, the legendary L88, and by 1970, the absolutely monstrous 454 LS6. The prevailing wisdom was simple and seemingly unassailable. There's no replacement for displacement. Want to go faster? Build a bigger engine. It was automotive gospel, carved into the stone tablets of every speed shop in America. A big block Chevy made 375 to 450 horsepower right from the factory. Small blocks? They topped out around 370, with the hottest factory combinations, and that was with compression ratios that demanded premium fuel. But here's where it gets interesting. In machine shops and garages from Pomona to Pennsylvania, something strange was happening. Racers were pulling cylinder heads off wrecked medium-duty trucks, heads with casting numbers like 461, 462, and the legendary 492. These weren't performance parts. They were designed for dump trucks and delivery vans, built to survive hundreds of thousands of miles of commercial abuse. General Motors never intended them for racing. They were about as sexy as a lunchbox. The first guy to figure this out was supposedly a racer named Junior Thompson from Oklahoma City, though 3 different states claim their local hero discovered it first. Thompson couldn't afford a big block for his '55 Chevy drag car. Working as a mechanic at a Chevy dealership, he noticed something odd about the heads on the medium-duty truck engines. The combustion chambers were smaller than standard small block heads. Much smaller. A standard small block head from a 327 or 3M50 had combustion chambers around 76 cc. These truck heads, they measured 58 to 62 c. That difference might sound trivial, but it changed everything. See, compression ratio is the difference between how much air-fuel mixture you can cram into a cylinder versus how small you can squeeze it before ignition. It's measured by comparing the total cylinder volume when the piston is at the bottom versus when it's at the top. More compression means more power from the same amount of fuel. It's free horsepower, essentially. With standard heads, a 327 ran about 10.5.1 compression with flat-top pistons. Bolt on these truck heads with their tiny chambers, and suddenly you're looking at 12.1, even 13.1 compression. That's race engine territory. The kind of compression that turns pump gas into power numbers that shouldn't be possible from 327 cubic inches. Thompson bolted a set of these heads onto a relatively mild 327, nothing special, just a standard bore block with a decent cam. On the dyno, it made 385 horsepower. That was big block territory from a small block. But the real advantage wasn't just the peak power. A big block 454 weighs about 685 pounds fully dressed. A small block 327, 440 pounds. That's a 245-pound difference hanging over your front wheels. In a sport where every tenth of a second counts, where launching hard without spinning the tires determines who wins, that weight difference was everything. The science was beautiful in its simplicity. Force equals mass times acceleration. If you want more acceleration with the same force, you need less mass. Every pound you remove from a car is a pound you don't have to accelerate. But weight on the nose of the car? That's even more critical. It affects weight transfer during launch, determines how hard you can leave the line without lifting the front tires completely off the ground. So what was actually happening inside these engines that made them so special? The combustion chamber is where the magic happens. It's the space above the piston when it reaches the top of its stroke, where the spark plug ignites the compressed air-fuel mixture. The smaller this space, the more you're compressing that mixture. When gasoline and air get compressed, they heat up. More compression means more heat before ignition, which means a more violent, more complete burn when the spark plug fires. These truck heads, designated as camel hump heads by racers because of the distinctive shape of their casting marks, were achieving compression ratios that Chevrolet's own performance engineers said required expensive racing fuel. Except they weren't using racing fuel. They were using careful tuning, precise timing adjustment, and occasionally water injection to control detonation. The 461 and 462 castings became the most sought-after cylinder heads in grassroots racing. They featured 2.02-inch intake valves and 1.60-inch exhaust valves, the same size as the high-performance heads. But those tiny 62cc chambers transformed everything they touched. Racers were pulling them from truck graveyards, paying $50 for a pair of heads that could transform a mild small block into a giant killer. Let me put this in perspective. A factory 396 big block in a Chevelle SS ran the quarter mile in about 14.5 seconds at $100 mile price. That was respectable for a street car in 1968. A properly built 327 with camel hump heads, the right cam, and careful tuning, 13.9 at 102 mm. In a lighter car like a Nova or early Camaro, you could dip into the 13s consistently. The technical revolution went deeper than just compression. These small blocks could rev. While big blocks started running out of breath around 5,500 RPM, a properly built 327 would sing all the way to 7,000 RPM, some even higher. Horsepower is torque multiplied by RPM divided by 5,852. If you can rev higher while maintaining torque, you make more horsepower. It's that simple. The valve train in a small block was lighter, more responsive. The shorter stroke meant less piston speed at any given RPM, which meant less stress on the rotating assembly. You could run more aggressive cam profiles, keep the valves open longer, flow more air at high RPM. Everything about the small block architecture favored high RPM operation. But wait, there's more. The intake manifold technology was evolving rapidly. While big block guys were still running dual-plane intakes designed for street driving, small block racers were experimenting with tunnel rams and high-rise single planes. These manifolds looked like someone had grafted a skyscraper onto the engine. The Edelbrock TR1Y tunnel ram, introduced in 1969, put two 4-barrel carburetors about 8 inches above the engine block. The long runners gave the incoming air charge tremendous velocity, cramming mixture into the cylinders like a turbocharger without the turbo. On a 327 with camel hump heads and 12.5.1 compression, a tunnel ram could push power past 400 horsepower from 327 cubic inches. That's 1.22 horsepower per cubic inch, a specific output that wouldn't become common in production cars for another 30 years. The carburation was critical. While big blocks gulped fuel through massive 780 or 850 CFM carburetors, The small blocks needed precision. A pair of 500 CFM carbs on a tunnel ram, properly jetted and synchronized, could deliver exactly the right amount of fuel at exactly the right time. Too much carburetor and you'd bog off the line. Too little and you'd starve for air at high RPM. The sweet spot was narrow but devastating when you found it. The camshaft selection became an art form. The Crane 290H, the Isky 505T, the competition Cam's 292 Magnum. These weren't just parts, they were weapons. Each had its own personality, its own power band. The 292 Magnum, with its 501-inch lift and 292 degrees of advertised duration, turned a small block into a high-winding terror that would pull hard from 3,500 to 7,000 RPM. Now, here's the kicker. While the factory big block guys were limited by warranty concerns and emissions regulations, the small block builders had no such constraints. They were building engines GM would never dare sell to the public. Compression ratios that required 103-octane fuel. Cam profiles that made the engine idle like a paint shaker. Valve springs that could control the valves at speeds that would scatter a factory engine. The pistons told their own story. Factory big blocks used cast pistons, fine for street use, but prone to failure under extreme conditions. The grassroots small block builders were using forged pistons from companies like TRW and SpeedPro. These could handle the tremendous cylinder pressures of 13.1 compression without cracking. They were lighter too, reducing reciprocating mass, allowing even higher RPM. The connecting rods were another revolution. While factory rods were adequate, racers discovered that GM's pink rods, identified by a pink paint mark and found in certain 1968-1972 applications, were actually stronger than the standard units. They'd been shot-peened for stress relief and could handle 7,500 RPM pulls all day long. Again, junkyard parts outperforming purpose-built racing components. The exhaust system science was evolving rapidly. Headers with 1.58-inch primaries and 3-inch collectors were becoming standard. The primary tube length was critical. Too short, and you'd lose low-end torque. Too long, and you'd kill top-end power. 30 inches from the exhaust port to the collector became the magic number for a high-winding small block. The stepped header, where the primary tube diameter increased part-way down its length, was discovered almost by accident when a racer fixed a cracked header with a larger piece of tubing. Think about that for a second. A cracked header repaired with whatever was lying around the shop became a performance breakthrough that's still used today. The ignition systems were pushed to their limits. Factory points-based distributors couldn't deliver accurate spark timing above 6,000 RPM. The points would literally bounce, causing misfires. Electronic ignition systems from Mallory and MSD solved this, delivering a precise spark at engine speeds that would have been fantasy just years earlier. The MSD 6A box, introduced in 1970, would fire multiple sparks at low RPM for better combustion, then deliver one hot spark at high RPM. It was space-age technology for guys building engines in their driveways. The cooling systems required complete reimagination. High compression means heat, lots of heat. The standard 180-degree thermostat was thrown out in favor of 160-degree units. High-flow water pumps from Edelbrock and Moroso moved 50% more coolant. Aluminum radiators with 4 rows of tubes replaced the standard 3-row copper units. Electric fans replaced engine-driven fans, freeing up another 15-20 horsepower that wasn't being used to push air. But the real genius wasn't any single component. It was the system, the combination, the understanding that every piece had to work together. You couldn't just bolt on camel hump heads and expect miracles. You needed the right cam to take advantage of the compression, the right carburation to feed it, the right exhaust to let it breathe, the right ignition to light it off. Miss any piece of the puzzle, and you had an expensive collection of parts that didn't work. The consequences for the automotive industry were immediate and profound. General Motors' own racing division was getting embarrassed. Their carefully engineered big block combinations were being outrun by engines built from salvage yard parts. The Z28 Camaro, originally built for Trans Am racing with a 302 cubic inch small block, suddenly became the template for a new kind of performance. High-winding, lightweight, technically sophisticated, rather than simply large. The NHRA and other sanctioning bodies had to create new classes. The old cubic inch base classifications didn't work when a 327 could outrun a 454. Weight-to-power ratios became the new standard. Factored classes were invented to level the playing field. The rule book grew from 20 pages to 200 as officials tried to keep up with the innovations. Insurance companies took notice. A big block muscle car commanded huge insurance premiums. They knew what those engines could do. But a small block? That was just a regular engine, right? Racers could insure their small block sleepers for a fraction of what big block cars cost, then go out and hunt big blocks every weekend. The aftermarket exploded. Companies like Edelbrock, Holley, Crane, and Competition Cams went from small specialty shops to major corporations. The demand for performance small block parts was insatiable. Every magazine had articles about building small block power, hot rod, carcraft, popular hot rodding. They all featured monthly buildups showing readers how to extract big block power from small block displacement. The technology transfer was remarkable. Techniques developed in backyards and small shops found their way into Detroit's engineering centers. Variable valve timing, high-flow cylinder heads, tuned length intake runners, concepts proven by grassroots racers became standard on production engines decades later. Consider the GM LS engine family introduced in 1997. It's essentially the ultimate evolution of everything learned from those camel hump heads and tunnel rams. High-flowing cathedral port heads, deep skirt blocks for strength, 6-bolt main bearings, compression ratios that would have required race gas in 1968, but run fine on pump gas thanks to better chamber design and engine management. The DNA of those junkyard-built terrors lives in every modern GM performance engine. The cultural impact went beyond just racing. This was democratic horsepower. You didn't need a trust fund or a factory sponsorship. You needed knowledge, patience, and the ability to spot good parts at the salvage yard. It was blue-collar engineering at its finest. Every guy with a garage and a toolbox could be competitive. David could beat Goliath if David did his homework. The stories became legendary. The kid who bought a wrecked cop car for the 327 rebuilt it with truck heads and went on to become division champion. The father-son team that built engines in a 2-car garage and supplied half the racers at their local track. The elderly machinist who could port cylinder heads by hand better than any flow bench could measure. These weren't corporate success stories. They were American success stories. Innovation born from limitation. Excellence achieved through understanding rather than spending. The proof that with enough determination and intelligence, you could compete with anyone. The technical lessons learned echo through modern motorsports. Today's NASCAR engines make 900 horsepower from 358 cubic inches. That's 2.5 horsepower per cubic inch, naturally aspirated. The foundation for that incredible specific output? High compression, excellent cylinder heads, precision valve train control, everything pioneered by guys bolting truck heads onto small blocks in 1968. Formula One engines in the naturally aspirated era made 3 horsepower per cubic inch by spinning to 19,000 RPM. Impossible without the valve train technology, the breathing efficiency, the systematic approach to making power that started in American drag strips with salvaged cylinder heads. But perhaps the most lasting impact was philosophical. This movement proved that engineering excellence wasn't about having the most. It was about understanding what you had. It showed that innovation could come from anywhere, that the next breakthrough might be hiding in a scrapyard, waiting for someone smart enough to recognize it. Today, When a modern enthusiast builds a 400 horsepower LS engine for $3,000 using factory takeoff parts and careful selection, they're following a tradition established by those camel hump pioneers. When someone posts on a forum about making big power on a small budget, they're part of a lineage that goes back to Junior Thompson and his salvage yard revelation. The big block versus small block debate still rages in some circles. There are still those who insist that displacement is king, that torque beats horsepower, that there's something indefinably superior about a big block's grunt, and they're not entirely wrong. For certain applications, towing, marine use, pure straight-line acceleration from a standing start, displacement has advantages. But the small block revolution proved something more important. It proved that smart beats big. That understanding beats spending. That innovation beats imitation. It established a particularly American form of engineering genius, practical, democratic, results-oriented, and absolutely unwilling to accept that expensive means better. Modern engine development, with its computer modeling and million-dollar flow benches, might seem far removed from guys porting heads with die grinders in their garages. But talk to any engineer at GM's performance division, and they'll tell you stories about some old-timer who could feel things in an engine that no computer could measure. They still consult with grassroots racers, still pay attention to what's winning at local drag strips, still understand that innovation doesn't always come from corporate R&D centers. The emissions regulations of the 1970s nearly killed this kind of experimentation. Compression ratios dropped to prevent nitrogen oxide formation. Cam profiles got soft to smooth out emissions. The factories retreated from performance, but the knowledge survived in those garages and speed shops. When the dark days ended and performance returned in the 1980s and beyond, it came back stronger because of what had been learned with those camel hump heads. Every modern fuel injection system that adjusts timing on the fly to prevent detonation is applying lessons learned from guys who figured out how to run 13.1 compression on pump gas. Every variable valve timing system is chasing what those radical cam profiles achieved mechanically. Every high-flow cylinder head design owes something to the porting pioneers who figured out that bigger isn't always better, that velocity matters more than volume. The heart of this story isn't really about cylinder heads or compression ratios. It's about the moment when American hot rodding grew up, when it went from bigger is better to better is better, when it proved that knowledge and innovation could overcome cubic inches and cubic dollars. Those camel hump heads are collector's items now. A good pair of 462 castings can sell for more than a complete running engine. They're not really competitive anymore. Modern aftermarket heads flow better. Modern pistons and rods are stronger. Modern engine management makes their crude compression approach obsolete. But they're cherished because they represent something pure. The moment when ingenuity triumphed over brute force. The next time you see a classic muscle car at a show, look closer. If it's a small block car running times that seem impossible for its displacement, chances are its owner knows this story. Chances are they understand that horsepower isn't about what you can buy, it's about what you can build. And chances are somewhere in that engine is the DNA of those truck heads that changed everything. That's the beauty of American hot rodding. It's never been about having the most money or the biggest engine. It's been about having the biggest ideas and the courage to try them. Those grassroots racers with their junkyard heads didn't just beat big blocks, they beat the system. They proved that in America, knowledge really is power, and power, when properly applied, is horsepower. What's the most unlikely combination you've seen dominate at your local track? Drop a comment below and share your David versus Goliath story. And if you enjoyed this deep dive into grassroots engineering genius, make sure to subscribe because we're just getting started exploring the untold stories of American horsepower.